All right, so next up when we're talking about forces, specific forces, because the other day we looked at our normal force, the force of gravity. We're always looking at applied forces, which is when we're figuring out our F net, our net force. Now, one of the forces we have that's a common one is called the force of friction. F and a little f, big F for force and a little f for friction. Friction is a force that resists motion and only occurs when two objects are in contact. I'm going to elaborate that on a little bit. Now, here's the key, and somebody mentioned this last class last day, is that the force of friction is always in the opposite direction of an object's motion. All right, so it never helps you out, friction, in terms of moving something. It's always working against you. All right, now there are two types of friction. There is static friction, and that is the force that tends to prevent a stationary object from moving. And then there's kinetic friction. Now that word kinetic is going to show up a lot in the next couple of weeks, but kinetic it's like a Greek word that refers to motion, and so kinetic friction is the force that acts against an object's motion in, again, a direction that is opposite to that of motion. So essentially, you've got static friction when something isn't moving, kinetic friction when something is moving. All right, now because of that, this is something that some of you may know, is that static friction is always greater than kinetic friction. And so if you've ever tried to push, say, a car, I had my license when I was 16, and I didn't have the nicest car, that's for sure, and sometimes you had to push it. Well, getting it started, overcoming that static friction was a lot tougher than when you get the car moving. All right, so getting something moving is always tougher than keeping it moving. Now, as I mentioned, that friction is when you have two things in contact, and pairs of materials encounter different results with respect to friction. That's something we're going to talk about here shortly, or I'm going to show you shortly. I got the C page 53. That is the page that I posted in Google Classroom. I'm also creating a formula sheet for you guys for this test coming up. All right, now what it's called is the coefficients of friction, or formulas for friction. And essentially we've got the same two formulas, they just look a little bit different, in that you can find your force of friction is equal to, you take what's called mu s, weird little letter, again, Greek letter, mu s, and you times it by our normal force. All right, and I'll get down to what mu s is here in a second, because it's very similar in that we have a second formula here where F of F, again, our force of friction. Well, we also have a mu k, which is your coefficient of kinetic friction. Again, I'll talk about that here shortly, times Fn. So essentially these formulas are the same, except for, again, what mu s is called your coefficient of static friction. And this mu k, well, I'm just going to almost say the same thing here, where mu k is equal to your coefficient of kinetic friction. Again, the formulas work exactly the same. It's just the situation you deal with. So again, this is the coefficient of kinetic friction. Now, what does that mean, right? So as I said, I have that page 53 here posted in Google Classroom. I've got it right here. Here's your coefficients of friction. So what's going on here is this is a rating. Coefficients are a rating. There's no units on them. It's just a rating of how much friction would be between two items that are rubbing against each other. So we've got different things like rubber on ice, Teflon on Teflon, Teflon on steel. You can see there is a bunch of different ratings. Now, there's two coefficients of friction for each of these, because you have one where the objects are not moving, and then you have the other where the objects are moving. All right, so that's our coefficients of friction. And again, they're just a rating system of how much friction there is. For instance, steel on steel greasy is 0.05 if they're moving. but steel on steel when they're dry, it's 0.41. So there's more friction when steel on steel is dry compared to when it's greasy, which obviously makes sense. Just like rubber, let's see, we have steel on ice. Aluminum on, no, I guess I don't have steel on ice like a hockey. Oh yeah, there it is, steel on ice. Very low coefficient of friction, but yeah, wood on wood, for instance, is much higher. All right, now how do we use these things, right? That's the key. So we get to example number 1. A large money safe, which is 128 kilograms, made of steel, is pushed across a wood floor. Calculate the force of kinetic friction. All right, so again, I always like to write out the information that I have and what I need to know. So it's telling me I need to find this force of friction. That is the kinetic force of friction. All right, there we go. Now my mass, it also tells me this safe is 128 kilograms. All right, so there's a couple pieces of information. Now, it also says steel is being pushed across a wood floor. So what I can go to is that table, my mu k, my coefficient of kinetic friction, and the two materials I have are steel and wood. All right, so I'm going to go to my page 53 here and check out steel on wood. I've got to find in my table, and look at, I got 0.25 and 0.45. Well, because these things are moving, it's going to be 0.25 is my coefficient of kinetic friction there. All right, so I needed my table here, and so I have 0.25. All right, now, when I'm looking at my formula, so we don't have everything we need here. We're going to have to do a little extra work here. F of F is equal to mu K times Fn. Well, we don't have Fn. We have mu K, but we've got mass here. Now, this comes down to what we were looking at the other day with forces. Is every object here, I have my 128 kilograms, but every object pulls down with a force of gravity, which we looked at calculating is equal to m times g. Now, because this safe is not flying up into the air and it's not going down through the floor, that means the vertical forces, the up and down forces, are balanced. And so Fg and Fn have to be equal to each other because, again, this safe is pushing down on the floor, and Newton's third law, the floor is pushing back up on the safe with Fn. So if we find Fg, we got Fn. All right. Now, again, Fg is mass times g. Well, we know our mass is 128. Our g, well, we're on Earth here, is 9.8. That's always the same. Now, when I multiply those two, what do I end up with here? I get 1,200 and what do we got? 54.4 newtons. All right, so now I got enough information to find my force of friction here. So I'm going to substitute in my values. So I'm finding my force of friction. My mu k, I found from the table there, it was 0.25. And my force of, normal force, which is again the floor pushing up on the safe, was 1,254.4 newtons. All right, and then I multiply those two together, and let's see here. I get, again, going to two decimal places, I get 313.6, and again, we're talking about a force, newtons. There we go. Any questions about that one at all? So we're kind of tying in some of the stuff we did before with the normal force and the force of gravity balancing each other out. Again, because this safe isn't going anywhere horizontally, or sorry, vertically. Horizontally, it's moving. All right, what else we got here? A child riding a plastic Jeep, total mass of 38 kilograms, applies the brakes and experiences a force of friction of magnitude 120 newtons. Find the mu k. All right, so what do we got here again? Again, writing down my information I know. My mass, 38 kilograms. All right, we know the force of friction this time out. All right, it's 120 newtons. And what we're looking for is find that mu k, I guess. All right, so now, again, we're going to use our formula here. Force of friction is equal to mu k, funny looking letter, times our normal force. But again, this kid's in a plastic Jeep, total mass of 38 kilograms. So just like I had last time, that Jeep is not flying up into space or going down into the ground. Thank goodness for the child. And so again, what's happening here is the Jeep is pushing down on the ground with a force of Fg. And because it's balanced forces, Fn, which is the ground pushing up on the Jeep. And because they're balanced, these two guys got to be equal, just like last time. And so I'm going to do the same thing I did last time, where I take my mass, which is 38 kilograms. All right, and I times it by my G value, which is 9.8. All right, let's see. I multiply those two together, and I get, let's see here, 372.4 newtons. All right, so now I'm ready to substitute in my formula. Again, I had to use that balancing out vertical forces again. All right, so my force of friction is 120. That mu k, we don't know. That's what we're trying to find out. And looks like my force of friction here, or normal force, sorry, is 372.4. There we go, 40, same thing. All right, now I want to get mu k by itself, so I'm going to have to divide both sides here by 372.4. So what I do to one side, I do to the other, so 372.4. All right, so these guys divide each other out. And so let's see here, mu k, that's our rating. There's no units here. I take 120 and I divide it by 372.4. What do I get here? I get 0.32. There we go. And as I said, no units because it's just a rating of how much friction would be between a plastic Jeep and whatever this child is riding on. Probably asphalt's my guess. All right. Let's see here. We're heading to example number 3 here. Let's see here. A horizontal force of 600 newtons is required to keep a car moving with a constant velocity. Okay. If the car weighs, we got the weight this time, not the mass, 7,840 newtons, what is the coefficient of friction between the road and the car? All right. So lots going on here. So let's draw what's going on here. There is an applied force on this car, and it is 600 newtons. All right, now here's the key, and this came up the last day, constant velocity. When you have a constant velocity, it means you're not speeding up, you're not slowing down, and so horizontally, our forces have got to be balanced, which is a nice way of saying that our force of friction here is also 600 newtons. All right, so that's one thing I have here. Now, the car weighs 7,840 newtons. That's a nice way of saying your Fg, that's your weight, is 7,840 newtons. But as we looked at before, this car is not flying up into the air, it's not going into the ground, and so our Fg is equal to our Fn, our normal force. So the car is pushing down on the road with a force of 7,840 newtons. And Newton's third law says the road is going to push back up on the car with 7,840 newtons. And that pushing up, again, is called our normal force. And once again, we are looking at mu k. That's what we're looking for, the coefficient of friction here. All right, so again, I'm going to use my formula. Had a little bit of physics to figure out first here. So I have, again, my force of friction is equal to mu k times our normal force. All right, our force of friction, again, because there's constant velocity, the horizontal forces have to be balanced out. They have to equal each other. All right, so we have 600 left, 600 to the right. So 600 is our force of friction. We have our mu k. Our normal force, which again is equal to the weight, 7,840. All right, and last step, we're going to have to, just like we did the last example here, divide by 7,840 to get mu k by itself. And what I do to one side, I got to do the other here, 7,840. All right, so again, these two divide each other out. And so it looks like our mu k between the road here and the car is, let's see here, 600 divided by 2 decimal places. I'm getting 0.08. And that, again, no units, because it's a rating on the amount of friction between this car and this road. Looks like it might be a little bit of a greasy road, because that is a low coefficient of friction.